After deriving the shear force and bending moment equations, now we would be in a better position to draw shear force and bending moment diagrams. So we have got the beam having a UDL applied. The reactions has been shown over here. First of all, we draw the shear force diagram. As we discussed that the shear force is varying linearly and it's a first degree curve. So at x is equal to 0, we get shear force equal to WL by 2, which is positive. So we have a positive shear. Please remember, positive, according to sign convention, our sign convention is facing down. So what we are saying is that the reaction which is facing up and at a very incremental distance from the support, we have a shear force which will be facing down. And that shear force is positive. After that, we start moving towards the mid span. So the variation should be varying linearly. At x is equal to L by 2, our shear is equal to 0. After that, our shear becomes negative until it reaches to the right support, and then it becomes 0. At the right support, our shear is minus WL by 2. So we can plug x is equal to L over here in equation 1, and we get shear as minus WL by 2. In a similar way, we can draw the bending moment diagram. The bending moment diagram would be 0 at the supports, and we can see that the equation gives us 0 bending moment at the support. We can put x is equal to 0 in the equation and the moment comes out to be 0. At the midspan, we have the maximum bending moment, which is WL square by 8. From the support till the midspan, our variation of bending moment should be parabolic. This is because the equation of bending moment is parabolic. After x is equal to L by 2, there would be a reduction in the moment, and the moment will keep on reducing until we reach to the right support where the bending moment would be 0. Please note that in case of beams which have got shear becoming 0 between two supports, will have maximum moment at shear equal to 0. This will not be true if we have a fixed support at point A and a free support at point B. Now, just few words about the coordinate x which we introduce in our system for drawing shear force and bending moment diagram. The coordinate x, in accordance with our sign convention, should have origin at the left support. Please note that x will extend to region of beam between concentrated forces and moments, or region with no discontinuity of distributed loading. In this example, we have got a uniform load applied. There is no discontinuity in the loading. That is why the coordinate x can capture the whole beam between support A and support B. In the case of concentrated loading, we will need 2x coordinate for capturing the whole beam. One coordinate x would describe the region between the two concentrated loads, which is this reaction, and the applied load, i.e. the region AB. And the second coordinate x will describe the region BC, which is between P and the right reaction. That is why we say that x extends to region of beam between the concentrated forces. So now this is another example which we will discuss, and this will make the concept related to coordinate x more clear. In this beam, we have the concentrated applied load and the concentrated reactions. Applied load and reactions, they are all considered as an external effect on this beam. Beside this, we have a UDL applied at the portion AB of the beam. Thus, in the case of this beam, we need three axes to define the whole beam. When we say to define the whole beam, we mean that to get the shear force and bending moment equation for the beam, the first x coordinate will capture the region AB where the UDL is continuous. After point B, the UDL become discontinuous. That is why region BC require another x. Region CD has got concentrated load effects at the boundaries. Hence, it would require another x. So please note that the coordinate x having an origin at the beam left end extends to the region of the beam between the concentrated forces or couple moments, or where there is no discontinuity of distributed loading. Instead of this concentrated load, we could have a concentrated moment applied or a couple over here, and again we would have required a new x to define that region. If there was another load between the region CD, then we would have required two x's to define the region CD. It is important to keep in mind that we should avoid using the transverse section which coincides with the location of a concentrated load or couple. So we can't take x right at the point where we have a concentrated load or a couple. This is because the point of concentrated load or couple represent a point of discontinuity in the variation of shear or bending moment. The first step is to determine the external reaction, and as discussed, the external reaction can be determined by taking summation of moment first at C and then at A equal to 0, or other way around. After this, we take arbitrary region AA between AB. Notice that we will start from the left point A, or in other words, the origin of our x coordinate would be the left support. At AA, we can have reaction, we have the applied load, which is uniformly distributed, and we put the internal shear and moment. After this, we take summation of Fy equal to 0, remembering that the load facing up are taken as positive. This will give us VAB equal to 63 minus 20x, and that is a first degree equation. Similarly, we can take the moment at point AA, which will be equal to 63 times x minus 20 times x into x by 2, and that will give us the equation of moment for the region AB. Because of discontinuity of this load, we will introduce a new x starting from point A, and now we will try to find out the moment and shear at BB. So again, the shear is 63 minus 20 times 5. So the full magnitude of the UDL has appeared, and that will come out to be equal to minus 37. Since there is no load in the span BC, therefore we will have a constant shear in the span BC. After this, we will find out the moment at BC. So the moment at BC would be 63 times x minus 20 times 5, which is 100, into x minus 2.5. So the lever arm of this UDL is x, which is starting from the left support, minus this portion, which is 2.5. This will give us the moment BC equal to minus 37x plus 250. Please note that the shear is constant and the moment has come out to be first degree, which is a straight line. Finally, we will take section CC in CD. The reason we need a new x for section CD is that CD is the region of the beam between concentrated forces. So we CD equal to 63 minus 100 plus the reaction 67 is equal to 30 kilonewton. Again, in CD, there is no variation of shear. So we have a constant value of shear. MCD at section CC will be equal to 63 times x minus 100 times x minus 2.5 plus 67 times x minus 10, which is shown over here. So we have three loads which are contributing to our moment CD. From here, we will get 30x minus 420. Please note that moment again in this region is of first degree. Now using this, we can draw the shear force and bending moment diagram. So for AB, we have the shear force 63 minus 20x. At x is equal to 0, we get 63. At x is equal to 5, we get a negative value of shear, which is shown over here, that is minus 37. Please note that at A, shear is positive and at B, shear is negative. That means to say that shear will be 0 somewhere in between AB. In order to find out the location of 0 shear, we can put VAB equal to 0 in equation A. And from there, we will get x is equal to 3.15. For the case of BC, the shear is constant as 37. Please note that at x is equal to 5, we should get the shear value minus 37, and that 37 based on our VBC equation should stay constant until we reach C. If AB is not giving us the same shear at point B as BC, then that means that there is some mistake, and most probably that mistake is in the reaction. It is important to note that at point B there is no concentrated load applied. Therefore, equation A and C gives us same value at point B. If we had a concentrated load applied at point B, then there would have been a jump in the shear at point B. In the case of region CD, we have a concentrated load at point C. Therefore, the shear at C determined from VBC will not be the same as shear at point C due to CD, and that is very clearly seen in this equation. The VCD is 30 kilonewton positive and VBC is minus 37 kilonewton negative for the whole region. Based on this argument, we can appreciate that the concentrated load is a source of discontinuity in shear, and therefore we need two x coordinates to define the region. One x coordinate define the region before the concentrated load, one x coordinate define the region after the concentrated load. In a similar way, we can work out the moments. The moment at AB is 63x minus 10x squared. So it's a parabolic distribution. As we discussed, if we have a shear force becoming zero within a span between two supports, then our bending moment will be maximum at the point of zero shear. Thus, we can put the value of x is equal to 3.15, which we worked out by making VAB equal to 0, and get our maximum moment. Please notice that the bending moment diagram within the region AB is parabolic. This will stay parabolic until the boundary of region AB. After that, it will become a straight line. Since we don't have any external moment or external couple applied on the beam, we can say that the bending moment diagram will be continuous. In other words, there won't be any jump within the bending moment diagram. This was not true in the case of shear, where we had concentrated loads applied and that caused a jump. By jump, we mean that at a particular point we have two values of shear. This is a very important point to check after drawing the shear force and bending moment diagrams. So to reiterate, if we have concentrated loads applied within the span, then the point of application of the load, we will have a jump, i.e. we would have two values of shear at that point, whereas the moment will be continuous. In the case of region BC, we worked out our first degree moment as minus 37x plus 250. If we put x is equal to 5 in equation D, we should get the moment value as 65. Thus, equation B at the boundary B must give us the same value of moment as equation D at the boundary B. If we don't get the same value in the case of moment, then that would mean that we have made some mistake. Normally, the mistakes are in finding out the reactions. If the reactions are not in equilibrium with the applied load, we will get nonsensical values for shear force and bending moment diagrams. We see in the region BC that the moment is varying linearly until we reach point C. At point C, which is the boundary of two regions BC and CD. Thus, again, our moment equation for BC at point C must be equal to the moment equation for CD at point C. As we discussed, this will not be the case if we have an external moment applied or a couple applied. In the case of couple, we will see the same jump as we saw over here. We will see the same jump in the bending moment diagram as we saw in the shear force diagram. So we have got minus 120 and minus 120 at point C. We must make sure that the moment equation for CD must give us 0 at the support D, which is the free support. At free support, our moments and shears drop down to 0. Please note that the internal support will have moment, whereas the external support has got 0 moment.